All right, welcome. In this explainer, we're basically going on a mission to take a sample of some mystery water and figure out how to make it safe to drink. We're going to cover everything you need to nail this for your GCSE exams. Okay, so you've got this sample of water. Is it safe to drink? I mean, how can you be sure? It could be from a river, the sea, even a puddle. Just by looking at it, you have absolutely no idea. And that, right there, is the whole point of Required Practical 8. So, here's the game plan. We'll kick things off with a super important definition. Then, we'll get our hands dirty and analyze our sample to see what's really in there. After that, we'll purify it and then wrap up with the key things you absolutely have to remember for your exam.
First things first, let's get our words straight. You're going to hear the word potable a lot, and it's so easy to get it mixed up with the word pure. Trust me, examiners love to catch people out on this, so let's make sure that's not going to be you.
Potable water is quite simply water that's safe for us to drink. That's it. It is not chemically pure H2O. Think about your tap water. That's the perfect example. It's totally potable, but it's got dissolved minerals and other things like fluoride in it. The whole point is that the nasty stuff like harmful microbes and crazy high levels of salt have been taken out. Okay, now this is the bit examiners absolutely love to test you on. Potable water has stuff dissolved in it. Pure water, on the other hand, is only H2O molecules and nothing else. You'd find it in a lab, not flowing from your kitchen tap. So if an exam question asks you to define pure water, your answer is simple. It contains only H2O molecules.
Right, let's get stuck into the practical side of things. We're going to analyze our water sample. Before we can even think about purifying it, we need to have some idea of what we're dealing with, right? First up, we're going to check the pH. See, water that's safe to drink should be pretty much neutral, which, as you know, is a pH of 7. The acceptable range is usually somewhere between 6.5 and 8.5. If our water is way too acidic or way too alkaline, that's a massive red flag straight away.
And you've got a couple of ways to do this. You could add a few drops of universal indicator and just match the color to a chart. That gives you a rough idea. But if you want a much more accurate, precise reading, you'd use a digital pH probe. That'll give you an actual number, a direct reading.
All right, next up, we're going to do a bit of detective work. We're going to find out just how much solid stuff is hiding dissolved in our water. You can't see it, but it's in there. And this practical shows you exactly how to measure it, a key skill you'll need to be able to describe. Now, the method itself is actually pretty straightforward, but you've got to be careful with every single step. First, you weigh a clean and, really importantly, dry evaporating basin. That gives you your starting mass. Then you add a specific amount of your water, say 50 cubic centimeters. You then heat it gently, and gently is the key word because you don't want it spitting and losing any of the solids. Once all the water's gone, you let it cool down completely, and then you wait again. The difference in mass has to be the solids that were left behind.
And here's where it all comes together. The math is super simple, right? It's just a subtraction. You take the final mass, that's the basin plus the solids, and subtract the starting mass of the empty basin. So 54.85 minus 54.50 gives us 0.35 grams. Easy. But listen, you must show you're working out in the exam.
Okay, now for the main event, the purification. We know there are solids dissolved in our water, so how on earth do we get the pure water out and leave all that other stuff behind? Well, the answer is a really powerful technique called distillation.
So this is the classic setup, and you've got to know what each bit does. You've got your flask with the water sample, which you heat. Then the steam travels into this long glass tube called the Liebig condenser. That's the bit that's cooled with running water. You've got a beaker at the end to collect your pure water, and a thermometer to check the steam is at 100 degrees Celsius, water's boiling point.
So how does this whole thing actually work? Well, it's a two-part process, really. First, you boil the water. Now, the magic here is that only the pure H2O turns into steam. The dissolved salts and solids have much, much higher boiling points, so they get left behind. Then, that pure water steam travels into the cold condenser, where it gets cooled down and turns back into pure liquid water. This stuff you collect at the end, that's called the distillate.
Now, this is a huge evaluation point for your exam. Distillation works brilliantly in a lab, but can you imagine the amount of energy it would take to boil enough water for an entire city? That's why it's a really expensive way to produce water on a large scale, like they do in desalination plants in places like the Middle East to get fresh water from the sea. It just costs a fortune in energy.
And there we have it. Mission accomplished. We've analyzed the water, we've measured what was in it, and we've purified it. So let's do a final debrief on the essential facts that you need to have locked away for your exam. Okay, this is your final checklist. Make sure you know the difference between potable and pure. That's a big one. You need to be able to describe the two tests, checking the pH and evaporating to find the mass of dissolved solids. For distillation, just remember the two stages, evaporation, then condensation. And don't forget it needs a ton of energy. Oh, and finally, for large-scale water treatment, fresh water is usually filtered and then sterilized with something like chlorine to kill any microbes.
And to leave you with a final thought, a little challenge for your revision. Imagine you've collected your beaker of clear, distilled water. It looks perfectly pure. But how could you prove it? What test could you do to show that it is truly pure H2O and not just potable? Have a think about that one.